Okay guys, welcome back to another GCSE Maths lesson. I believe this is the 8th one. Today we're going to be covering the first part of probability. So there are two parts of this. The second part is going to be the extremely difficult kind of exam questions that you can come up with. But this first part is going to be mainly about conditional probability. So things like, and it's not just going to be the kind of probability tree diagrams. So make sure you stick around for that. For the first one, it says there are only red marbles and green marbles in a bag. There are 6 red and 4 green. Mason takes at random a marble from the bag. He doesn't put it back into the bag, and he takes a second one. Complete the tree diagram. So what I would like, again, with probability kind of questions, it can help to draw out a diagram. So we have 1, 2, 3, 4, 5, 6, and we'll put little R's in here. So 6 red, and then we have 1, 2, 3, 4 green ones, right? So the way these tree diagrams work is this is the, when he puts his hand into the bag and pulls out a marble, right, there's a chance that it's red and there's a chance there's going to be green, okay? And then if it's red, then the next time he puts his hand in, you have those two possibilities of it being, again, red and green. And likewise, if it's green, then these two. So basically it shows you all of the different outcomes from pulling out, in this case, 2 marbles from a bag. So, good evening, Evie. How are you? So essentially, all we need to do here is work out, before he's pulled out the first marble, what are the odds of him getting a red versus a green? Well, in total, when we work out probability, we look at the number of ones that we want divided by the total number of outcomes. So that's a very fancy way of saying, okay, so there are 6 red marbles, so I know the top of my fraction is going to be 6. Now, how many marbles do I have in total? Well, there are 6 red and 4 green. Therefore, in total, there are 10. Okay. Likewise for green. Well, there are 4 greens, and in total, there are 10. Now, one thing to note about probability tree diagrams, this is a good way to check if you've done it correctly, is that across the branches, it should add up to 1. Because all probabilities add up to 1. So 6 over 10 plus 4 over 10 gives me 10 out of 10, which is 1. So we're correct there. Now here's where it gets a bit tricky. Okay, let's look at the first possibility where when he pulls out the first marble, it's a red marble and he doesn't put it back. So if we wanted to draw that out, we could just put a line through here and say, well, he's gotten rid of 1 red marble. So now when he's pulling out the second one, what's the probability of him getting a red and a green? Well, how many red marbles do we have left? Well, there's 1 fewer, so there's 5 now. So 1, 2, 3, 4, 5. So the top is now going to be 5. Now, how many are there in total? Well, we've taken 1 marble out, right, from this first section here. So there's only 9 left. Okay, and again, if we counted up the marbles here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the mistake that I tend to see students make is that they don't take away 1 from the top and the bottom, right? So if a red marble is taken, then the number of reds decreases by 1 and the total number also decreased by 1. Okay, now likewise with the green, well, there are still 4 greens left because we didn't take a green out of a total of 9. And again, if we look across the branches here, 5 at 4 is 9, so we have 9 out of 9, which is 1. Now what happens if he took a green marble? Well, the number of reds doesn't change, so this is still a 6. But the total number has decreased to 9. And likewise with the greens, now it becomes 3 over 9. Another question I get asked is if we have to simplify the fractions. So you don't have to with probability tree diagrams because it gets a bit tricky to realise, like they need to ideally be the same. So you don't need to simplify them, okay? And it in some cases helps to not simplify them. Hopefully that all makes sense. Again, I don't think probability tree diagrams are too tricky. There's just a few things you have to remember. And again, the questions are going to get more tricky as we go along. Perfect. So part B, it says work out the probability that Mason takes 2 marbles of the same colour. And again, this is another place where students tend to make mistakes. Okay, the first thing you need to do is write out the different ways that he could take 2 marbles of the same colour. So in this case, he can either take out a red followed by a red, or a green followed by a green. Now it might seem fairly obvious in this question, but in some questions it can get a bit tricky. Make sure you eliminate every possible way of fulfilling this condition. Okay, so red and a red, what we're going to do is read along this probability tree. So he picks a red, then another red. Now when we go across the tree, like along it here, we times the probabilities. So in this case we'll have 6 over 10 multiplied by 5 over 9. Another way to look at it is we want the probability of getting a red and another red. Now whenever I say the word and in probability, it means times. Okay, so the other way of writing this would be probability of one red and, so I put a times, a probability of getting a second red. Okay, 6 times 5 gives me 30, 10 times 9 gives me 90. Now I'm going to have to add probabilities together, so I'm not going to simplify it just yet. What about green and a green? Well, we start off at this probability here, and it's 4 out of 10. And multiply it by this probability, which is for the second green, 3 out of 9. Now, here's where some students get a bit confused. They think that this is the answer, but it's not. Okay? So, in order for me to get 2 marbles of the same colour, I can get a red and a red, or a green and a green. Now, whenever I say the word or, I need to add. Okay? So, probability of the same colour is the probability of getting 2 reds, 30 over 90, or, so add, the probability of getting 2 greens, 12 over 90. And again, the reason for that is because, sorry, I've got a bit of a cold, so I might sound a bit under the weather. Where was I? Okay, so because we're saying that there's 2 different ways of it happening, we need to add those probabilities together. Okay, so in this case it's 42 over 90. You can simplify if you want, but you don't have to. Okay, so you can say it's 21 over 45. I believe you can divide that by 3 as well, right? So 7, 14, 21, that becomes 7, and that becomes 15. And that's as low as you can get. Either way, you don't have to simplify with probability, usually, unless they specify. So again, I don't think that was too tricky, but again, the questions will gradually, very slowly get harder and harder. Okay. So even here, this is slightly more difficult. This is something called conditional probability, okay? And I'll explain why in a second. So each day, Paul either wears a red or a black tie to work. On Monday, the probability he wears a black tie is 0.6. Okay, so I'm going to put that in right now. Probability on a Monday is 0.6. Okay. Now, if it says here, he either wears a black or a red tie, those are the 2 options. So if the probability of him wearing a black tie is 0.6, then the probability of him wearing a red tie is 1 minus 0.6. And the reason for that is our probabilities have to add up to 1. Okay? So, if Paul wears a black tie on Monday, the probability that he will wear a black tie on Tuesday is 0.35. So black tie Monday, so black tie on Tuesday is 0.35. And again, we need to make sure it adds up to 1, so that means the red tie will be 0.65. So the reason why it's called conditional probability is this here is a condition. If he wears a black tie on Monday, that's a condition. Then the probability changes. Okay? So the probability depends on what happens on Monday. So it's a condition, okay? But it's really not that complicated. It doesn't really matter. If he does not wear a black tie on Monday, the probability that he will wear a black tie on Tuesday is 0.68. So again, we can fill that in. And again, it needs to add up to 1. So all we need to do is do 1 minus 0.68, which is 0.32. Those are our 2 marks. Are there any questions on that at all? It's just all about really reading quite carefully. Oh, good, perfect. So again, they're gradually getting a bit more tricky, but not too bad so far, I hope. And again, work out the probability Paul wears different coloured ties on Monday and Tuesday. So again, this is where students can get a bit worked up in terms of the probabilities. So he has to wear a different colour tie. So one red, one black. So he can either wear the black tie on Monday, followed by the red tie on Tuesday, or you can wear the red tie on Monday and the black tie on Tuesday. Now there's no other combinations, right? Because either he wears two black ties or two red ties, which isn't a different colour tie. Bear with me 1 second. Okay. So again, we can work out these probabilities now. Black tie on Monday, 0.6. So let's put 0.6 here. And then, because we're moving along the tree, we times that by the red tie on Tuesday, 0.65. Just so you're aware as well, is the first question we did can turn up on non-calculator or calculator because it's fractions. But with decimals, it's only going to be calculator paper. Okay, unless they're really easy decimals, but these ones aren't particularly easy. I'll work those out both together in a minute. Red then black, we have 0.4 multiplied by black, which is 0.68. So again, if you notice, I'm hesitating when I'm saying it, because again, it needs to be red then black. Some students multiply the wrong probabilities. They go red and red, or something, or black and black, for example. So now we can pull up our, whoops, not that. It's Cortana. Pull up our calculator. Perfect. So 0.6 multiplied by 0.65 gives me 0.39. And then we also have 0.4, so 68, which is 0.272. But again, the probability of wearing a different colour is both of those things added together. Okay, so answer plus 0.29 gives me 0.662, and that's our final answer. And again, that's 3 marks. You might notice it doesn't really take 3 marks worth of time, but again, it's all about effort. Probability tends to be one of the trickier topics because people can lose marks without really noticing. Okay, so these kinds of questions are the most common for students to kind of lose a mark or two because they don't include all the probabilities or something else. Okay, so it's very easy to make a mistake. Everything okay with that one? I think that's all okay. Again, it gradually gets more difficult, so if you're finding this easy, that's good. Perfect. Thank you, Evie. So again, this one, so you may have noticed in the previous questions, it kind of holds your hand a little bit, right? It takes you through it. But this one is just a 4-mark question, straight away. You have 5 red, 3 blue counters. 2 counters are taken at random. Work out the probability that one of each colour is taken. 2 ways to do this. Okay. The first way is to do what was given in the previous question and draw a probability tree. The other way is I like to draw a little diagram. There are 5 red counters. There are 3 blues. So I can do the probabilities in my head fairly easily, but that's because of practice. But again, you can draw a probability tree. Now, if we want to one of each colour, either a red is taken then a blue, or a blue is taken then a red, right? Now let's have a think about the probability. So I'm going to do this without doing a probability tree because we've already because I want to show you a new way of doing it, because in the previous questions we've already done probability trees, okay? So, probability of taking a red, right, is going to be the 5 reds we have, so 5, over the total number of counters, 1, 2, 3, 4, 5, 6, 7, 8. And then again, don't forget, we need to multiply, because it's a red and a blue. Now, if we've already taken a red, we can put a line through a red. Now, what's left over? Well, we have our 3 blues over 7. Okay? So again, you don't need a probability tree. But again, this is just a different way of doing it. If you want to use a probability tree, that's a valid method, okay? So, we've done that possibility. And again, I'll work it out in a second. So, probability of getting a blue at the beginning is the 3 blues we have over the total number of counters, which is 8, multiplied by the 5 reds we have over the 7 that would be left over if I were to cross out blue. All okay with that? Again, just stop me if you need any help with that. 15. And we can cool. Might notice it's actually the exact same probability, but once again, one of each color, so one of each. Well, either one of those methods works, right? So we're going to take the red-blue probability and add it to the blue-red, because it's either or. It doesn't matter. And that is a 4-mark question done in 3 lines. So you can use a probability tree. That's valid. We can do it this way. Is this method okay? Is there any questions about that at all? Okay. Good. We're getting through these pretty good, yeah. Perfect. Thank you, Evie. Perfect. Okay, so 4 more question. Oh, hello, Lila. Perfect. All good. Okay, now here it gets a bit more tricky, right? Because we have 3 colours. Okay? So there's a few more combinations, but it's the same maths, okay? So again, let's draw a diagram out. So we have 1, 2, 3, 4, 5. These are reds. We have 1, 2, 3 blues. And we have 1, 2 greens. Again, if you want, we can do a probability tree, but it's going to be a pretty big tree. But Billy takes 2 counters at random from the bag. Work out the probability that both of the counters are from the same colour. Good. So either it's 2 reds, or it's 2 blues, or it's 2 greens. Fairly standard, I think. I think that's okay. For 2 reds, well, how many reds do we have at first? Well, we have 5. And how many counters? We have 5, 6, 7, 8, 9, 10. And again, because it's and, we need to multiply. And we get rid of one of the reds. We have 4 reds left over. And there's 9 counters left over. Again, just feel free to stop me if any of this doesn't make sense. Two blues. Well, we have 3 blues at the start out of 10. Then one of them goes away, so it becomes 2 over 9. So again, you can see that you can start doing this a bit faster and faster and faster, okay? But only once you're comfortable. With the greens, we start out with 2 over 10. And then 1 over 9. So again, feel free to digest that and stop me. I'm just going to work out these fractions. Okay. Now once again, we're looking for the probability that both counters are the same colour. Not that they're red, red, blue, blue, or green, green. Right? So we need to add all of these together. So 20 over 90. So 20 add 6 is 26, plus 2 is 28, 90. And again, you don't have to simplify if they don't specify. Okay, so I think that's okay so far, hopefully. Again, that was a 4-mark question, done pretty quickly, I think. Okay. Okay, so in this one they actually give us the diagram. Okay, so I'm just going through a bunch of different style of questions, and they should be in general getting harder as we go along. So Helen takes a card at random. She does not replace it. Helen then takes another card at random. So far, all of our questions have been this. They don't replace, okay? Now, if they don't say that they replace it, then assume that they don't replace it, okay? If they replace it, something different happens. So you need to be very careful that it says this, or that it doesn't say they replace them, okay? There's a question coming up, I'm pretty sure, that has one where they replace it. The probabilities change slightly. Like, think about what would happen, okay? Then takes another card at random. Both cards have the same number. Well, either it's going to be a 1, 1, or a 2, 2, or a 3, 3. Okay? What about probability of getting a 1, 1? Well, at first they make 2 out of 7. Right? So there's 2 1s out of 7 cards. Then one of the 7 goes away. So we have 1, 1 left over, 1, 1, out of 6 total cards. 2, 2, once again, it's 2 over 7. And it'd be 1 over 6 again because there's only 2 cards. Cross one out, left with that. 3 3s, we have 3 over 7 at the beginning, multiplied by 2 over 6. So again, make sure you can see where I'm getting all these fractions from, just while I work this out. So we have 2 over 42. We have 2 over 42 again. Then we have 6 over 42. And once again, it's asking for probability. Both cards have the same number, so uh, 2 plus 2 plus 6 will be 8 over 42. So again, we're doing these questions pretty quickly. Now the second part, this is the style of question that can get a bit more interesting, okay? Definitely a higher paper question, definitely towards the end. So calculate the probability that the number on the second card Helen takes is greater than the number on the first card she takes. There's a... is that the answer to part B? Or... Oh! Well spotted, Evie. 2 plus 2 plus 6 is 10, not 8. I'm sorry. I'm dosed up on a lot of medicine at the moment. Yeah, that is completely correct. That is a 10. Well spotted. Cool. This isn't an actual exam paper, Lila, so I've actually gathered a bunch of questions from different exam papers and also from Maths Genie, okay? So this isn't actually a specific paper. In terms of what paper can it come up in? So it can come up in paper 1, 2, or 3. But mainly it's paper 1 or 2. Okay? If it has decimals, it's only paper 2 because it's calculator. If it's fractions, it can come up in paper 1 or 2. Okay? So calculate probability. Okay, so we have a bunch of different combinations, okay? So either, if she picks a 1 first, then the second card must be greater than 1. So it can either be a 2 or it can be a 3. Okay? If she picks a 2, then the second number has to be a 3. And she can't have picked a 3. Right? Because if she picks a 3, there's no number bigger than 3. Is that okay for the 3 combinations we have? Are there any questions about that? So again, the probability that the number on the second card, yeah, perfect. Sweet. Lila, I assume by no you mean there's no question, so good. So probability of getting a 1 and then a 2. So probability of getting a 1 was 2 over 7, if we remember rightly. Perfect. Thank you, Lila. And then getting a 2 afterwards. Well, if we get rid of a 1, we still have 2 2s left out of 6. So that would be 2 over 6. Likewise, if we have a 7, we have a 1 and a 3, so that would be 2 over 7 times, and we actually have 3 3s left, so that would be 3 over 6. I may not have left myself the most amount of space, but yeah. Then we pick a 2 first, so that's 2 out of the total 7. Multiplied by, well, we get rid of one of the 2s, and it has to be a 3, so 3 out of 6. So that will become 4 over 42. I'll try and make sure I can add basic numbers now. So 6 over 42. And this will also be 6 over 42. And then probability, I'm not going to write the whole thing out. It's going to be 4 over 42 plus 6 over 42, that's 10. So it'll be 16 over 42. This time I didn't make a mistake. That should be it. So again, slightly trickier. In terms of what they can ask you, this can be anything. Okay, so you have to be, if there's one thing to take away from the lesson, make sure you understand my logic. Because this kind of question won't turn up, but they'll change what the condition is. And unfortunately, there's basically an infinite number of conditions they can give you. Okay. This one's interesting. So 50 people asked if they like tea, coffee, and hot chocolate. And everyone liked at least one of the drinks. 17 liked all 3. Blah, blah, blah. This type of question, right, when they give you information like this, okay, it's always, so if I draw blocks here, you have to draw a Venn diagram. You have to. This information is way too complicated to try and piece together yourself. Okay? Hopefully you can see why. Mutually exclusive. Okay. So the term mutually exclusive. Actually, I don't know why I'm writing it. Mutually exclusive just means that both events cannot take place at the same time. Okay? So the word exclusive means that it's kind of apart from everything, right? Like an exclusive club means that certain people can't come in. Mutually means that it can't happen for both of them. Okay? So mutually exclusive means that both events cannot take place at the same time. So for example, if the probability it's raining tomorrow is 0.4, probability if it's sunny tomorrow is 0.6, those two events are mutually exclusive because they can't happen at the same time, for example. Hopefully that clears up your question. So we have to draw a Venn diagram. Is everyone okay? And this is a 5-mark question. Is everyone okay with what a Venn diagram is? Hope so. Okay. So what you need first is we need a circle for each of these 3 things, and they need to overlap. So this is where things get a bit messy. So we say that's for tea. Then coffee has to overlap. And then hot chocolate needs to overlap as well. H. So T is for tea. C is for coffee, and H is for hot chocolate. In fact, let's do HC for hot chocolate. Maybe that'll make it a bit more amenable. Cool. Now we have to read this one by one. So with Venn diagrams, you always start from the middle and work out. Venn diagrams tend to be something quite easy for students, but they always make mistakes in the exam. So again, those of you that are tuning in, I'm willing to bet you're pretty clever, right? And you can understand maths with a bit of help, okay? Which is fine. The problem is human beings tend to get a bit arrogant, right? And when we find something easy, we rush it and we make mistakes. when you come to sit your exam or your mocks or whatever, you'll find that you'll answer every question but won't get 100% because you've made mistakes. Okay? So, with this, it's so easy to make a mistake with this. It's unbelievably easy, okay? Really, really easy. So you start from the middle of the Venn diagram and work outwards, okay? So you work from the three-way intersection, then the two-way ones, then the outer ones, okay? Now the good thing is that this information is written in order that you should add it, okay? Actually, no, it's not. Never mind. You'd have to work your way out from this stuff, okay? Well, I'm glad that I've managed to give it to you. If you work from the outwards in, you won't get it correctly. So, for example, 31 people like hot chocolate, right? That's what it tells me. So, all of the numbers in the hot chocolate circle should add up to 31. So, we're going to have a number here, 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 and here. All four of those numbers should add up to 31. So starting from the out is basically impossible, right? I can't write 31 here because that's not true. The total is 31. Yeah, good. So you need to look at the unions, the intersections, okay? So just be very aware of that. Try and work your way from the innermost to the outermost. So the innermost is all three people, sorry, one person likes all three drinks. 17 people like all three drinks. There we go. Now, let's try and work out how many people like tea and coffee. So, okay, actually, coffee and hot chocolate, but not tea. So they like coffee and hot chocolate. So that would be this intersection over here is 2. Okay? Then 7 people like tea and hot chocolate, but not coffee. So they like tea and hot chocolate, so that'd be 7 over here. So far, is that okay? So this question is a bit tricky because they haven't actually given us some of the information. So sometimes they're quite nice and they would give us tea and coffee as well. But they haven't been very nice. Okay? So we don't know this number and we can't work it out just yet. Right? Actually, we can. Tea and coffee. We can work it out. Okay. So again, sometimes they give you directly what tea and coffee is like together, but we can actually work it out pretty easily. So, tea and coffee. So, it says here, so I also like to tick off the information as I use it, right? So I've used this, I've used this, I've used this. So now all I'm looking at is these 3 pieces of information. So again, I like to start from the in and work my way out. So let's look for the one that says and, which is this piece of information here. 21 people like tea and coffee, right? So what some students do is write 21 here. It's not correct. Okay? For tea and coffee, we're looking at the intersection between these 2 circles, which is both of these numbers here. So 17 plus the number in this bit add up to 21. So in this case, it's going to be 4. That's probably the first thing I've said that might be pretty tricky. Any questions about that? So Jemima, you're okay? Perfect. Lila and Evie, are you good with that? It's a bit tricky. So tea and coffee is this intersection here. That adds up to 21. Okay, perfect. Wonderful. So now we've done all of the inner bits, we have to now work out the outer bits. There is one thing we can say. Every person likes at least 1 drink, which means the number outside the circles is 0. Because everyone has 1. Everyone's in at least 1 circle. Good, I'm glad that that was okay so far. The next thing we realise is, let's look at the number of people that like tea. So 34 in total, right? So everyone in this circle here should add up to 31. Okay? So the number in here is going to be 31 minus 4 minus 17 minus 7. Okay? So 7, 17, that's 24, 28. So that's going to be 3. Hang on, have I... 7 and 17 is 24. 28, yeah. Oh, sorry, it's 34 people. My bad. So add on 3, that should be a 6. My maths was right, I just chose the wrong number. So the number in there is going to be equal to 6. Showing you the way I'm working out is helping. But again, stop me the second you don't understand. So we've used that piece of information now. One more piece of information. 31 people liked hot chocolate. Let's do the same thing. 31 minus 7 minus 17 minus 2. So 7 and 17 is 24. 26. So that should be equal to 5. Would there be an X in the middle of 17? In the middle of 17? As in the middle of this one, or when I was calculating it? So as in this middle 17 here, should there be an X, or when I was calculating it just now? Okay. So while you type that out, I'm just going to continue. So in the last bit, we need to work out how many people are in here. Ah, good question, Evie, yeah. So this counts as working out. Okay, so if you look, this is a 5-mark question. If you manage to do the probability by hand, as in writing out whatever that is, you would get 4 marks, but this is all method marks. So you get 3 marks for this Venn diagram, a mark for the probability calculation, and another mark for the right answer. Okay, good question, really good question. You get marks for the Venn diagram, okay, because this does take a long time. You get up to 3 marks for it. So with the coffee, so we use that information, where everyone likes 1 drink. So if we do 50, take away all of the rest of these numbers, so 4, we will get our final answer. You can still get method marks. So, for example, if I read this as like 40 instead of 50, there's something called error carried forward, something called ECF, which you'll see in your mark schemes, where if you make a mistake, they can reward method marks for the following parts. Okay, so you don't just lose all the marks. If I read this as 40 though, they wouldn't give any marks. They might give some error carried forward marks, but you'd lose a lot. So, yeah. So, you know what? I'm going to be lazy and just do this on a calculator. So 50 minus 4 minus 17 minus 7 minus 2 minus 6 minus 5. 9. Perfect. That makes my life easier. Cool, so we've gained most of the marks already. So all we need to do now is work out the probability that they both like coffee if 50 people are chosen at random. So the number of people that like coffee are all of these people in the diagram here. So we have 9 plus 4 plus 17 plus 2, 13, 30, 32 people. Probability that they both like coffee, it's going to be 32 over 50. Now they won't choose the same person again, so we subtract 1 from the number of people that like coffee and 1 from the total number of people. Okay, and once again, should be a calculate paper question, but if it's not, it doesn't matter. 992. You can do this by hand, I know, but I don't think you want to watch me just do like you know, column method multiplication. So 2,450. And that is 5 marks. Long question, not going to lie. But it is 5 marks, so it's expected. You can do this Venn diagram a lot faster than what I did. Bear in mind, I spoke through everything I did. So I'm willing to bet you guys can eventually write this pretty quickly. Any questions at all about that? Hoping that's okay. Good. Yeah. Another question, which is pretty annoying. It's another Venn diagram question, but you know, it's good to kind of practice. Apples, bananas, and oranges. So let's just real quick blast this one out. We'll start a bit faster than this. Sorry for stumbling over my words. Like I said, I'm a bit sick. So apples, it's nice. I'm trying to make sure that my overlap is big enough that you guys can actually read what's happening. This box. Okay. So once again, we'll start from the middle. So it's roughly in order of when we're going to use it. 11 people like all 3, so that makes our life slightly easier. And again, tick off the piece of information. 33 people like apples. Again, I like to work my way out, so I'm going to skip that. 6 people like apples and bananas, but not oranges. So apples and bananas is here, not oranges. So that should be 6 there. Right? Because again, we're not including the people that like oranges, so they shouldn't overlap. Okay. So 15 people like bananas and oranges. So again, that's in total, so this should be 4. Because again, it doesn't specify that they don't like apples. 5 people don't like any fruit. So those people are going to go straight outside the Venn diagram. And all 25 people who like oranges like at least one other fruit. So that means all 3 numbers here should add up to 25. 11 plus 4 is 15. 10. So where does the 4 come from, Lila? Okay. So it tells me here 15 people like bananas and oranges. Okay? Now all the people that like bananas and oranges are in this intersection here. Those 2 parts. So those 2 numbers should add up to 15. Does that make sense, Lila? Okay, perfect. Does the 10 make sense? I did hurry through that explanation just to get to Lila's question, so... Cool. Sorry for that noise, by the way. I've muted it. Okay. Now we can start working our way out, right? So 33 people like apples is where that 6 is. Not quite. It would be A and then the N symbol B and not C. Because you're saying it's or not C, right? So it would be something similar to this. So where does the 4 come from? Okay. So if you look here, Jemima, it says that 15 people like bananas and oranges. So if we look at where bananas and oranges, we're looking for the overlap between bananas and oranges, which can you see as this overlap here. So the bit right in the middle and the bit over here. Those 2 numbers should add up to 15. So I knew that 11 plus something had to add to 15. That something had to be 4. Does that make sense? So I hope that makes sense. Okay. So 33 people like apples. So everything in this circle here should add up to 33. Currently I have 10 plus 11, which is 21, plus 6, which is 27. So to get to 33, I'll need another 6. Hope that makes sense. Okay. Now, if you want, you can actually write a 0 in where this part is. Because again, everyone that liked oranges liked other fruit as well. Okay, so there's 0 in just the oranges. So now, everyone else needs to be in just the banana circle. So we're doing 50 minus 5 minus 6 minus 6 minus 11 minus 10 and minus 4. And that will give us everyone that's left over, which is in the banana circle. So 50 minus 5 minus 6 minus 6 minus 11 minus 10 minus... Again, you can do this in your head. I'm being a bit lazy. And that's our Venn diagram. We did it a lot quicker, but we can do it even faster. It says here, 2 of the 50 people are chosen at random. Work out the probability they both like bananas. So, how many people in total like bananas? Well, we have 8 plus 6 plus 11 plus 4. Okay, so 6 plus 4, 10, 21, 29 people. So you have 29 out of the total 50. Multiplied by, we subtract 1 because they're not going to pick the same person twice, over 49. And let's just use a calculator. Again, you can do this by hand. And if you want me to show you how to do it, I'm more than happy to. But I think everyone in here is okay with column multiplication. 58 over 175. I think that's too bad. Any questions about that at all? I think that's okay. Okay. All good. Perfect. So we only have 10 minutes left, and I actually split probability in 2. Okay? Probability can be one of those unseen super hard questions. The ones where they have like algebra in it and ratios and all this other stuff. We're going to do that next week. There's no point in me doing it now because we only have 10 minutes and it gets a bit more intense. But the stuff we've mainly covered today is probability trees and the Venn diagram kind of questions. So those should hopefully be okay. But next week is the hardest probability questions you'll find. Okay? So I'm not looking forward to it. But again, if you get good at it, it's going to be, yeah, it is exciting. But probability is really easy to lose marks on. Because, again, you can miss out on one combination and you'll get the wrong answer. You'll get method marks, don't worry about that. But it is where pretty much all students will lose at least 1 mark. Okay? So if you get like 98% in your test, you'll know why. It's probably a probability question. But again, only 10 minutes. I don't think it's fair for me to just shove this in now. You guys have worked really hard, so we can finish slightly early. But next week we'll definitely go through the harder probability. Thank you, Lila. I really appreciate it. Honestly, at the moment, it's just a bit of a... It just hurts to talk. So everything else is pretty much fine. It's worth studying, yeah. But honestly, so this is going to sound a bit cringy, but probability is more of a mindset. Okay? It's less equations and more thinking logically about what they're asking you to do. What are the combinations? What are the situations you're in? Okay? So, yeah. It's a bit more bit more of a mindset than it is calculations. Okay. But yeah, it's one of the tricky ones. After probability, I want to ask you guys, what would you like to do next? So vectors is probably the hard. Actually, vectors is one of the tricky ones as well, so we can do vectors for sure. I know it's in all 3 papers, Evie. And it's definitely likely to come up in at least 2. So that, like, the length of a line, we can do that. We can do that. Yeah, it's. I think they just call it coordinate geometry. That's just what they call it. But that has like everything in it, just everything, like midpoints, equations of lines, perpendicular bisectors, all that. Also includes like lengths of lines as well. Yeah, I can do ratios. Yeah. So ratios, length of line. Yeah, cool. So I'll write those down. We will cover everything, but some topics are pretty. Some people just don't care about them, so no one really tunes in. So I don't bother doing them just yet. I will say that soon I'm going to be doing topic summaries of the whole. There are 7 topics in GCSE Maths. I'm going to do big topic summaries of all of them. So you have like algebra, numeracy, ratios, etc. Yeah. Okay. Again, I think vectors is pretty tricky, but we can save that for a bit later. This covers the next 3 lessons now, so it's fine. Okay. If that's everything, I hope you guys enjoy your evening. You're probably on half term, at least I am as well. So enjoy your half term. Take a bit of a break. Okay, don't work too hard. And yeah, you're very welcome. But yeah, definitely don't work too hard. Burnout is very real. Okay, you can drive yourself a bit crazy. I appreciate that. Thank you both for your kind words, and thank you for tuning in as well. It's always good to see you guys. Yeah. Then definitely take a break. Okay? Definitely. If you get burned out, you're going to do really badly in the exams, even if you know what to do. Take some time off. Okay? I know you probably got set a ton of homework, but you know, take a bit of a relaxing break. Although the weather's terrible. Very welcome. Yeah, perfect. I will see you guys. Yeah, so I'll see you guys next week. Again, enjoy your half term. You've definitely earned it. And yeah, we'll cover the harder parts of probability, and then we'll probably go on to length of lines or ratios and things like that. Yeah. See you guys later.